Okay, let's dive right into this. Welcome to today's explainer, where we are absolutely mastering the ultimate exam strategy for the Cambridge AS and A-Level Computer Science 9618 syllabus. Specifically, we are tackling a beast of a topic, the system clock. Now, I want you to think of paper 2 like a marathon. Seriously, it's not a sprint. It requires pacing, it requires energy management, and most importantly, it requires a rock-solid, unbeatable strategy for how you construct your answers over the long haul. Today, we are going to break down the actual academic benchmarks and those complex, multi-step calculations that Cambridge examiners are desperately searching for. We're going to take those expectations and turn them into your absolute biggest advantage on exam day.
Right, I need you to look at this number on the screen. 15%. That is not just some casual throwaway statistic. The system clock, along with its associated theoretical foundations, accounts for approximately 15% of the total marks in Paper 2. Think about what that actually means. That is effectively an entire grade boundary resting entirely on your understanding of this single topic. If you're one of those students who has been treating the system clock as just a minor hardware definition, something to quickly memorize and then completely forget, you are literally leaving massive, massive points on the table. Examiners point this out year after year. They constantly highlight that students really struggle with the analytical depth and multi-step calculations required here. But before we continue and fix that, make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Hit that button so you don't miss out on these insights, because by the end of this explainer, you're going to know exactly how to claim every single one of those marks.
Here is our roadmap for today. 1. Core principles. 2. Technical methodology. 3. Critical evaluation. And 4. Examiner warnings.
Section 1. Core principles, focusing on academic benchmarks and cross-topic links.
Listen, the theoretical architecture of the system clock doesn't just exist in some isolated bubble. It's connected to everything. And this quote, straight from the Principal Examiner Report, proves it. Candidates referencing cross-topic connections achieve significantly higher marks. That's the secret sauce right there. Integrating the system clock with other areas of your syllabus, like memory read and write cycles or the fetch-execute cycle, shows the examiner that you actually get it. It signals that you understand computer science as a massive, interconnected ecosystem rather than just a bunch of disjointed definitions you crammed the night before. When you can fluently link clock speed to overall system performance or identify potential bottlenecks in the hardware, you are demonstrating the exact analytical depth that Cambridge benchmarks demand for those top-tier grades.
And this brings us to a massive pitfall. This brilliantly illustrates one of the most fundamental areas of confusion examiners see every single year, mixing up cause and effect. In the context of the system clock, you have to keep these two completely separate in your mind. The cause is the clock tick itself. It's that continuous, oscillating electronic signal generated by the quartz crystal. That's the heartbeat. The effect, on the other hand, is the synchronization of all computer operations and the precise execution of instructions. If you write an exam answer that somehow implies the execution of instructions is what creates the clock pulse, your logic completely collapses and the marks vanish. The clock provides the beat, the entire system synchronizes to it, period.
Let's move on to Section 2, Technical Methodology and the Procedural Framework.
So, algorithmic thinking is the absolute beating heart of this syllabus. When you're sitting in the exam hall and you're faced with a multi-step calculation, you can't just guess. You can't just throw raw facts at the page and hope something sticks. Top students use this procedural framework every time. Step 1. Step-by-step decomposition. You break that massive, intimidating problem down into logical, bite-sized pieces. Step 2. Appropriate data structure selection. You pick the right tool for the job. Step 3. Efficient code implementation. And Step 4. Rigorous testing to verify your results. This standardized sequence is exactly how you tame the chaos and extract meaningful conclusions from raw data under extreme exam pressure.
Now, pay close attention because this is absolutely crucial. We need to talk about the method mark strategy. Cambridge examiners award marks for the journey, not just the destination. If you do a complex calculation entirely in your head and you only write down the final answer on your script, you are walking a tightrope without a safety net. Seriously. Because if that final number is wrong due to some tiny, silly arithmetic error, you get a 0, completely wiped out. But if you execute your analysis with clear, systematic working, showing exactly how you applied the principles step by step, you can earn almost all the points, even if your final digit is a bit off. So please, I'm begging you, show you're working. Prove your logic to the examiner.
Okay, let's take a quick breather and test this out.
Imagine an exam question asks about the impact of upgrading the system clock in an automated factory setting, and a student simply writes, "A faster clock makes the computer run instructions faster." Can you spot the fatal flaw there? Think about depth. Think about context. While you ponder that, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve their grades, so hit that button right now. All right, back to our student's answer. Why does that generic response score a big fat 0? Let's break down the mindset you need to fix it.
Which perfectly transitions us into Section 3, critical evaluation and the top scoring mindset.
Look, a passing candidate can solve a problem, but a top-tier candidate? They evaluate the quality of their own solution using hard, evidence-based reasoning. This evaluative thinking is built on 4 massive pillars. First, considering multiple solutions. In computer science, there is rarely just one single way to solve a system architecture problem. Second, analyzing trade-offs. This is huge. If you increase the clock speed, do you sacrifice memory? Do you generate too much heat? Third, acknowledging limitations. What are the actual physical constraints of the hardware you're dealing with? And fourth, justifying your decisions with solid evidence. Evaluating performance isn't just theory. It is the core of practical application.
Let's make this super concrete with a direct comparison. On the left, we have superficial evaluation, the kind that gets you average marks. On the right, top scoring analysis. If you write, "It runs quickly," the examiner just rolls their eyes at the lack of depth. A top candidate doesn't say that. They identify specific time complexity. If you write "It uses memory," you get nothing. A top candidate analyzes space complexity. And if you literally write "It seems to work," you are just hoping for good luck. The top-scoring student explicitly tests boundary conditions and edge cases and discusses exactly how those affect system performance. You absolutely must elevate your vocabulary if you want to hit those academic benchmarks.
Section 4. Top Examiner Warnings. Let's talk about the classic mistakes you absolutely need to avoid.
Now, what's really interesting about this is that these 3 mistakes right here account for the vast majority of lost marks when it comes to the system clock. Mistake number 1, confusing cause and effect. We nailed this earlier. Do not mix up the clock signal with the execution of instructions. Mistake number 2, completely forgetting to check boundary conditions and edge cases when you're evaluating your algorithms. And mistake number 3, which examiners are constantly pulling their hair out over, providing generic, rote-learn answers that have absolutely zero connection to the context given in the actual question. Superficial breath is your worst enemy in paper 2.
Let's zoom in on mistake number 2 for a second. What exactly is an edge case? Well, by definition, it's a problem or situation that occurs only at an extreme operating parameter. Think about it. When you're writing an algorithm or analyzing how a system processes data, you can't just test the normal, happy path expected inputs. You have to ask the hard questions. What happens when the buffer is exactly at maximum capacity? What happens when the input is 0 or some massive negative number? Missing these boundary conditions and completely failing to explain their effect on overall system performance is a guaranteed one-way ticket to losing those high-level critical evaluation marks.
And here is the ultimate examiner alert. This answers our challenge from earlier. Look at the stark difference between a generic answer and a contextual answer. If the exam paper gives you a detailed scenario about, say, an automated warehouse logistics system, and your answer is just a perfectly memorized textbook definition of the system clock, you will not get the marks. It's wild, but it's true. The classic mistake is failing to link the theory to the real-world context. Every single point you make, every calculation you perform, must be directly applied to the scenario provided. You have to weave their specific information into your structured reasoning. Make it relevant.
Now let's be real. Exam conditions are highly stressful. Your cognitive load is going to be maxed out. You're going to be exhausted. So here is a super quick memory hack for exam day to help you recall all these complex causal relationships under pressure. Create a mnemonic using the first letters of key system clock terms. For example, to remember that procedural framework we talked about, you could use DSIT. Deconstruct, structure, implementation, testing. Creating these little mental shortcuts means that when you turn the page and see a terrifying 15-mark question on system architecture, you don't panic. You just unpack your mnemonic and immediately start building a structured, logical response.
Let's move to the finish line and see how all of this builds into one cohesive approach, the final system. Deconstruct, solve, evaluate.
All right, grab a screenshot of this or write it down, because this is your final actionable problem-solving checklist for the system clock. First, identify the given information. Pull out the binary data, highlight the specific context. Second, break it into logical steps. That is your decomposition. Third, solve systematically. Apply the methodology and show you're working to lock in those method marks. Fourth, check for reasonableness.
Did you test the edge cases? And finally, make justified recommendations. Use actual evidence to evaluate the performance. This is your roadmap. Use it.
Ultimately, knowing the strategy is only half the battle. Executing it under a time limit is the other half. Top-scoring strategies absolutely improve grades, but only if you practice them consistently with past paper questions. Students who implemented these frameworks see incredible improvements. So, here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. Join the community, get the strategies, and don't let another exam season pass you by without being fully prepared.
As we wrap up this explainer, I really want to hear from you. Head down to the comments right now and tell me, what is your target grade for computer science? And honestly, what is your absolute biggest challenge when it comes to the system clock or algorithmic thinking? Is it setting up those multi-step calculations? Is it tracking down those sneaky edge cases? Drop your thoughts below so our team can tackle them in our next masterclass. Keep practicing, keep evaluating your work, and I will see you next time.